Okay, come in. So welcome to the quantum session, last one of the day. And please come in, okay? First speaker is Yanbin Chen, is a joint work with Yannick Stade, quantum constant propagation.
Yep.
Okay?
Yep.
Please go.
Yep. Thanks for introducing. And I'm happy to be here to present our work, quantum constant propagation. Sorry. I think it would be very useful for you to give you a bit of background knowledge if you have not heard of what a quantum computing is. So let's start with the notations, very common notations which we will use in quantum computing. So in quantum computing, we often use CAD notations to denote column vectors. To give you an example, if you think of a space of complex vector of length 2, then actually we have two computational basis vectors denoted respectively by ket0 and ket1. In this sense, any complex vector of length 2 can be expressed by a linear combination of ket0 and ket1. We could also go to a higher dimension. Say we go to a dimension of 4. Then here we have four computational basis vectors, namely ket0, ket1, and ket2, ket3. However, here we use, as you can see, binary representation for 0, 1, 2, 3, which is also very common. Another common operation, which is tensor product or chronicle product, which is defined to be, if we have two vectors, v and w, then the chronicle product, v tensor w, is defined to be, we first just write out the vector v, each entry of v as it is, and then we attach vector w to each entry, and then we expand out the vector w. So in the end, we get a vector of dimension, which is a product of the two input vectors, a product of the dimensions of the two input vectors. Now, let's talk about quantum computing. So we all know about classical computing. So say if we have a classical computer with m bits, we know that we can use a binary value to represent the state of a single bit. So we can stack all these m bits together, and then we have a column vector of length m. So we use this to represent the state of classical computing. Then we have a circuit, which is a low-level representation of algorithms. The circuit acts upon the state, and then we get an output state, which is again a column vector of length m. However, things become different in quantum computing. Say if we have a quantum computer with n qubits, where a qubit is a quantum counterpart of a bit in the classical computing. To denote the state of a single qubit, we can only use a vector of length 2, a complex vector of size 2. And the initial state of the quantum computer is denoted by the tensor product of all the initial state. So as you recall from the definition of the chronicle product or tensor product, you will eventually get a vector of length 2 to the power of m. Then we have a circuit. We have a circuit, quantum circuit, which is also a low-level representation of quantum algorithm. This circuit acts upon this initial state, and we get an output state, which is again a vector of length 2 to the power of n. However, if you are careful enough, you will see that here I didn't explicitly express the output state in terms of each of the qubit states. This is because if you apply quantum gate, then qubits get entangled with each other. So in general, there is no way to separate qubits from each other. So there is no way, generally, to express the state in terms of individual qubits. So you can see from here how challenging it is to simulate a quantum computer in a classical computer. Because even denoting the state of a quantum computer needs an exponentially number of costs, let alone performing a computation upon it. Let us back to our point. Why do we propose our optimization? Currently, quantum gates are very expensive and yet very noisy. That is, if you perform a quantum gate, there is a chance that you introduce a noise into your state. So, to counteract this fact, the straightforward idea is to say, okay, we just wish our circuit to contain as less number of gates as possible. And we also wish the gates in the circuit to be as simple as possible. Generally, a gate is considered to be simpler if it acts upon less number of qubits. We will see what it means very soon. And we will perform, since this optimization is performed on a classical computer, we wish this optimization to be as efficient as possible. So in this sense, we kind of push some of work from the quantum computing to the classical computing, because the classical computing is a world which we are all familiar with, and we have many sophisticated methods, and there is no error if we perform a classical gate. Now the idea is that we can propagate initial configuration throughout the circuit, and then we take the information we propagate to simplify the circuit along the way. This is kind of similar or analogous to what we do in static analysis. If we try to simplify a function and we know that the input to this function is limited to a certain range or domain, then we know, okay, maybe this block of the function can be eliminated given this input. Let me give you a very toy example. So if we have initial configuration of all ket0 state, and we propagate this information to the point indicated by this dashed line here, then you can see that the middle gate, this gate, is actually redundant. Why? Because the information here tells us that the first two qubits, the top two qubits, is either 0, 1 or 1, 0. So one of the qubit is disabling the gate. So this gate will never be applied. So we can remove this gate entirely. After we have done so, you can see we can pairwise remove these two C0 gates, a C0 gate, these two X gates, these two C0, and these two hard mod gates, because those gates are both unitary and Hermitian. Then in the end, we will get a trivial transformation upon the quantum system. Even if I told you that this example is a very toy example, this optimization here I show you is not yet adopted by standard optimizer of the quantum of the existing sophisticated quantum circuit optimizer. So this also strengthens our contribution in this work. So how can we do this? So because as I have told you, it's exponentially hard to simulate the circuit. So actually, if we really wish to propagate the initial configuration throughout the circuit, it is also the equivalent to simulating a the circuit classically. So how can we achieve this? Let's look at some existing approaches. One approach, the relaxed peephole optimization. So they have an idea So they say, okay, we only track the state of each single qubit. So that is, they only track pure state. In this sense, they use an automaton where each node in it. It is disappearing. Why? Let me reconnect it again. Okay. Yeah. So where are we? So this RPO approach tracks only pure state, and like each node denotes some state of the qubit to be tracked, and it goes from one state to another if you apply a single qubit gate upon it. However, there is a drawback that once you apply a multi-qubit gate onto this system, you lose all the information. So as you can see, you will go from ket 0, you will go to the state of top, meaning you know nothing about this qubit because it gets entangled with the rest of the system and lose its purity. Another approach, EXO. So they say, okay, maybe at this point, so we simulate the circuit to some point, and then we just send this circuit up to this point to be executed onto the quantum computer for many shots so that I can get the probability distribution characterized by the state described here at this point. And I set a threshold, and I kind of drop all the peaks which is below the threshold so that in the end I can get another probability distribution which could likely, or could hopefully be approximating the original distribution, but the information density you need to represent the state is significantly lower. However, there are two drawbacks for this method. The one is that you need a quantum computer to perform this optimization. Another drawback is that you are leaving out some peaks. So kind of there is a risk of inaccuracy as you go on the simulation of your circuit. So our approach tries to counteract these drawbacks. Our approach can be performed entirely on classical computer. It can run efficiently, and it will not give up when some entanglement is formed. How do we do this? Basically, we kind of design and implement the data structure like this. So we have a table where each entry corresponds to each qubit, and initially each qubit is inside its own entanglement. If during the execution of the circuit qubits get entangled, we put these entangled qubits into the same union. And inside each union, we maintain only non-zero coefficients of the computational basis. In this sense, for this example, instead of using a vector, a complex vector of length 32, we only use 1, 2, 3, 4, 5 pieces of value to represent the state of our system. However, we also need to guarantee that our optimization can run very efficiently. So here we set a number, a max. So this is a threshold which we say, okay, if one entanglement gets just too complex, so that the number of non-zero coefficients in this entanglement is exceeding a max, then we set this entanglement to top, so that we give up upon only this entanglement, but we still have track upon the rest of the system. So by doing so, we can guarantee our optimization to run fast. Now, let's talk about how are we going to use the information we are propagating to simplify the circuit. Let's consider a few words on what a control gate is. So say a control gate is a gate like this. It has a control wire and a data wires. So if a control wire receives signal 0, then the gate is disabling, then this gate is not applied. If the control wire receives 1, then the gate is applied. Let's have a look how are we going to use the information we propagate to simplify our circuit. The first simple case is for a control gate to receive always gate 0. At 0 gates, then we know that this gate is always not applied, so we just remove the entire thing. In case we know that this wire, the input is receiving always 1 because 0 and negates of 0 is 1, then we know that this gate is always applied, so we can remove this control signal because we don't need it. We know already in advance that this gate is always going to be applied. So here, by doing so, we kind of simplify the complexity of the gate. Let's talk about a more complex case. So look at the state here, indicated by the dashed line. If you look at the first control, then you will find actually this control could be either 0 or 1, because it gets 0, 0, 1, 1. So actually the first case cannot be applied. And the second case can also not be applied because it is not always 1, it could also be 0. And the same reasoning applies to the second qubit. It could be either 0 or 1. But in this case, we could still do something about this gate. So if you look carefully enough, then you will find actually the information given by the first 2 qubits is implied by the third qubit. Because if the first 2 qubits are enabling the gate, then so is the third qubit. For example, if the first 2 are already 1, then the third one is always 1. If one of the first 2 qubits are disabling the gate, then so is the third qubit. So you can see if one of the qubit is 0, then the third qubit is also 0. So in this sense, we know that the first 2 controls are redundant, so we can already remove it. So this is the high-level idea of our implementation. We have implemented our quantum constant propagation as an artifact, and we wish to evaluate how it works. So we evaluate our optimization method on this Munich quantum toolkit bench. This is developed by one of the groups in Technical University of Munich. It has 28 algorithms, scalable in number of qubits, and in total 1,761 circuits. Because it is very normal for modern compilers to have multiple optimization passes and compose those passes together to get a better effect. So we wish to test how much more the overall optimization can achieve by composing in our optimization. So we consider 2 existing optimizers, PISC, Qiskit, and TCAT, and we wish to measure how many more gate count reduction and control reduction we can achieve by composing in our optimization path. And as you can see, in terms of gate count reduction and control reduction, by composing in our optimization path, these 3 existing optimizers can benefit very much. We wish also to compare our optimization with the RPO method. Recall that this RPO method is also taking the idea of information propagation, but it only tracks the state of pure state. It only tracks pure state, namely single qubit. And as you can see, either composing our path before or after RPO, the overall optimization can be facilitated. Actually, if you set the Nmax, that is the allowance for the entanglement complexity, to be 1 or 2, then our optimization can only track single qubit system, which is completely subsumed by RPO, which this fact is also demonstrated if you look at here at this column 1 and 2, at this column 1 and 2. So this is like by composing, if you set the Nmax to be only 1 and 2, then by composing in our optimization path, the overall case is deteriorating. But however, if you allow for a larger max, then actually the overall effect can be significantly improved. So this also showcases that our method is not subsumed, and it offers much more than already existing. We also wish to show that our optimization can run very efficiently. Here, to test these, we kind of choose the circuits for quantum Fourier transform with qubit number 2 to 129. The reason for that is this set of circuits grows quadratic. So the circuit in this set grows, the number of gates grows quadratically to the number of input qubits. And it also produces a very complex entanglement amongst qubits. So in this sense, if you try to simulate the circuit naively, these set of circuits guarantee to reach you a very complex and challenging case very soon. And looking at this plot of our runtime, you will see that actually, looking at this trend, our runtime only grows polynomially to the number of input qubits. And as you increase the allowance for the complexity of the entanglement, the time required to complete the optimization will be increased. However, you can see that even for the largest number of max and for the most complex circuit, our optimization can terminate, can complete its work within an acceptable amount of time. So as a summary, our optimization tries to reduce the circuit's complexity by removing superfluous controls and controlled gates. It does so by performing a restricted but computationally efficient simulation upon the circuit. The key feature of our method is that we kind of maintain a data structure which kind of separate entanglement groups in separate data blocks. But we also have to admit that our method is limited by the number of, by the value of Nmax, which is our allowance for the complexity of the entanglement. So if the circuit, one entanglement gets more complex, then our method will give up upon the entanglement. Okay, so thanks for your attention, and
thank you.
Yeah.
Thank you. Questions? Come on. Be entangled with the speaker.
So thank you so much for your talk. So I would like to ask you, does your method have a way to recover from the situation where you have top, let's say? Because I expect like the more you go further in the circuit, the more qubits will become entangled, and so at a certain point, maybe everything is top. And can you recover from this situation? Thank you.
So actually, there is existing method that can recover from the top. Let me show you. So if you look closely at the state, the automaton here, and you see you can go from top to some certain state, but this is achieved by programmers making some annotations inside the circuit. So if the programmer are sure about at some point the state of the circuit, then you can indeed recover some information. But this is not accounted for by our optimization because we kind of wish to rule out the influence of the programmers.
Okay. Other questions? I have one, maybe. In the last slide, you mentioned limitations, and in the slide before, in the 12, if you go to slide 12. 12.
Yeah.
Yeah. The shape in that corner on the right bottom corner is completely different. Is that because of the limitation and the entanglement grows?
Oh, you mean the one for 4,090?
That one, yeah.
Yeah, I would say it's still in, so because I think it's those outliers, so we kind of have to scale the graphics in a way that also includes these two.
Okay.
So,
no, that's the right.
But the shape are similar.
Okay. Okay, so let's thank the speaker. There's some time for another question.
So maybe a bit of a naive question, but like the way I imagine when you're doing quantum computations is that you get a lot of the advantage from these entanglements. So do you have maybe some kind of intuitive reason, because your approach, it still seems to manage this and it still seems to work. So do you have some intuitive reason to explain why kind of the states, even though they do entanglement, they don't get so crazy complicated that you can still handle it with your technique?
So just to repeat what you're asking, to make sure that I understand what you're asking, are you asking like if the circuit gets too, so the entanglement in the circuit gets too crazy, then is there any guarantee that my method can still handle it?
So I think the question, I guess, is more that like, how is it possible that kind of these algorithms that you took a look at don't get so crazy that the method does still manage to handle it? And kind of what's the intuition, or how, why do the algorithms not get so crazy entangled just a little bit?
Well, I think, so if the circuit gets crazily entangled, so the qubits in the circuit gets crazily entangled, then this is the situation where our optimization wish not to touch upon. Let me give you one justification why. So if you look at this method here, so this Axel method, they kind of, what they try to achieve is quite similar to what our purpose is, but they kind of drop out these low peaks at here. So in case where the qubits are crazily entangled, then the cases are which those peaks are on average very small. So there could be a case where the threshold is, it could be above all these peaks. So then you kind of drop out all the distributions that you have, then you lose anything. So kind of, it's even bad than top, because it's like you're losing all the valuable information on the system. So as you said, the quantum algorithm kind of benefit from those complex entanglement. So if the entanglement is truly entangled, is truly complex, and then we can kind of wish to keep it. So does it answer your concern?
Yeah. I mean, I can ask offline.
Yeah, sure.
Okay. I think it's okay. So let's send the speaker again.